Okay, Paige, we can start. We are live streaming.
Perfect. Thank you very much, Nicolay. And I would like to say welcome to the final event for C 2025 to all of our teams. My name is Paige. I'm the technical chair of C 2025. This is my second year as a technical chair. So I host the regular meetings. I help teach students and advise them along the way. And we had a lot of really great teams this year. I've seen a lot of really great ideas and accomplishments that I'm excited to share with you all today. So I would also like to say a quick thank you to our many sponsors and partners who do make C possible. This was Pitch, SISO, AWS. I try to put as many of you on the slide as I could. You all helped to make C possible, so thank you very much. We're also going to be having today a panel of experts. C is for educating students and networking as well. So we're very excited this year to introduce a panel of experts, both from professional organizations, universities, industry, who will be listening along today. And then at the end, we'll have a bit of a feedback and discussion session with them. So we're excited to have them join us today. Right now, I'd like to hand it off to Mike Conroy to say a few words before we get started.
Good morning, everybody. Welcome to SEE 2025. Been following along, and every year we see new ideas and systems that make SEE larger than it was before. This has continued year after year after year. It is absolutely fantastic. Along the way, I don't know if y'all realize it or not, but you're helping Earth's inhabitants, the folks here, create answers that are going to help us go move into space. SEE is focused very, very heavily and very, very closely aligned with our goals to get off the planet and see how far we can get. And also share that more than once, and Zach can probably chime in too, people have told us, no, you can't possibly do that. No, you can't possibly do this, or no, you can't possibly do that. And we've offered to, well, let the SEE students and let the teams show you exactly how to go do that. So you have been a tool that we have used over the years to nudge people to the direction of working together, how to go share information, how to go do things. Across the years, I've seen cable cars, greenhouses, bases, communication systems, different types of surveyors, rovers, habitats, launchers, prospectors, and much, much more in these sims. And it just continued and continued and continued to be something new. I can't wait to see what SE 2025 looks like. This is going to be grand. That's it, Paige.
All right, thank you, Mike. Now we're excited to move into
it. If I disappear, I've got computers rebooting all around me. There's just something bizarre going through my office right now. So if I disappear, it's not because I wanted to leave.
I promise I'll let you back into the meeting. All right, we're going to move on to the presentation portion. So this is when any of our teams are welcome to share a bit about their design, what they've accomplished this year, maybe a little bit about the simming graphics they've developed. So with that, we're going to start with Brunel. So I'm going to pull up your charts and then you can walk us through them.
Hello, Paige. Hello, everyone. Thank you.
Hello. All right. Can you see your slides?
Yes, I can see. Thank you for sharing. And yes, simulation exploration experience for 2025. We are from Brunel University. Next, please, Paige. And go to next slide. Thank you. A very brief introduction. My name is Maziar. I will be presenting on behalf of our team and modeling simulation group at Brunel University, London, UK. Our team consists of supporters, student lead, undergraduates, and postgraduates. Our support teams are Simon, Anastasia, Nora, and myself. Our student team is Hridianshu, and student team members are Fatma, April, Marek, Vasim, and Tracy. Page, next slide, please. Thank you. This year, Brunel team aim to collaborate more closely with C and other participating teams, enhancing our distributed simulation capabilities and gaining more hands-on experience with industry standards and industry tools. Our objectives are designing more robust simulations, focused mostly on collaboration and interactions this year. Next, please, page. Thank you. To achieve this, we designed 2 featherettes, one spaceport and a lander. This spaceport is a networking hub, also a physical entity that supports traffic in and out the lunar base. The lander is also a physical entity that transports astronauts and cargo to our spaceport and lunar base. Here are 2 baseball cards that we are showing. One of them is for the spaceport, another one for the lander. These baseball cards contain descriptions, behavior, design tools, and data elements for interactions. This year, our objectives will also work on 2 types of interactions, internal and externally. Next, please. In C, we also create interaction metrics to conceptualize interactions between our featherettes and participating featherettes. Along with other teams, we also conceptualize a simulation scenario with interaction phases. In this scenario, we showcase collaboration between 3 teams. From when the lander is approaching the spaceport and lands, and astronauts are transported to other facilities on Moon. Next, please. To achieve this, we structure our team into 3 groups: programmers, 3D designers, and 3D integrators. The 3D integrators are also responsible for testing and dry runs. We aim to document all our progress this year and make it available for the coming years. For the technology stack, we use Eclipse IDE, SKF Starter Kit, Blender, and thanks to C support, we were able to use tools from Pitch Technologies and NASA for 3D visualization, and very Dawn Distributed Observer Network is one of them. Next, please. Just to provide an overview of the infrastructure, we use Pitch RTI or runtime infrastructure. This infrastructure allows us to create featherettes and federation locally or join C federation remotely. This is a local configuration that we're showing here, involve not only our 2 featherettes, spaceport and the lander, but also other featherettes that make the distributed 3D visualization possible. Next, please. Thank you. To provide a summary, thanks to C support and other teams, we were able to overcome challenges and achieve our objectives. A few lessons, takeaway lessons, are creating platforms for knowledge sharing, which is very important, and early start, especially for collaborative simulations and interactions. Our future plan is to continue our participation in team and collaborate closely with other teams to create more realistic and immersive 3D visualizations and simulations. Next, please. Thank you. I just want to say thank you for your attention and this fantastic opportunity. Thank you. Back to you, Paige.
Excellent. Thank you very much, Brunel. Next, we're going to have Embry-Riddle Aeronautical University.
Hey, team. There we go. Thank you for presenting. This is our team. Austin, Christina, Sean, and I worked on something a little different. We decided to use Trick for our simulation this year. Unfortunately, we won't have featherettes joining the simulation due to some technical difficulties we ran into along the way. But we still accomplished a lot, and we're excited to share that with all of y'all. Next slide. We put together a kinetic launcher, lunar rover, and lunar emergency shelter. We have simulations going for the lunar rover and one for Chuck. Getting the HLA stuff integrated was where we ran into problems, mostly due to environment issues. But next slide. So Chuck is going to be our kinetic launcher, centrifugal hypervelocity universal cargo kinetic system. It's a circular rail system designed to accelerate payloads along a curved track using centripetal force. The idea is to spin the payload along a rigid curved rail and use that to transfer energy and achieve a high velocity launch without atmospheric drag. Once the payload reaches the target speed, it is released at the terminal point, and this launches it towards its predetermined trajectory. This leverages the benefits of rotational motion to create a compact, efficient, and robust solution tailored for the unique challenges of lunar operations. And the data elements we were working with here were velocity, angle of attack, and delta V, and our interactions we planned for this device were the lunar surface, launcher, and cargo. Next. The exploration excursion vehicle is a 7.5 by 10 foot vehicle with capability to seat 2 astronauts. Navigational equipment is primary, but accommodation for emergency supplies and instruments for experiments is also a factor in the design and development of this vehicle. The simulated behavior we were targeting was basically just lunar travel across the lunar surface. And data elements we were working with were position, battery level, communication, GPS and navigation, and mass. And the interactions we were targeting were the lunar surface, the crater, other surface mobility elements, and location. Next. And finally was our lunar emergency shelter. This was a mobile facility to provide astronauts in an emergency situation with a temporary shelter. The idea here was to deploy this vehicle prior to a mission, or to allow it to follow them while they're on the lunar surface. And the idea here is to ensure that astronauts have access to protection, supplies, and communication capabilities in case of emergency. The data elements here were protection, power, life support, and localized GPS, and interactions were with the lunar surface, the lunar base, and deep space network. And that is it from us.
Excellent. Thank you very much. Next university will be Fastens. One moment.
Hey, Paige, can you hear us?
Yes, I can hear you.
Okay.
All right, you should be seeing your slides now.
Okay. Next slide, please. So we are the Fastens team, and we developed a lunar transportation system called cable car. Our team includes the professors Andrea Braga and Fabrício Torquato, our team leader Rafael Ramos, and the developers Kaique and José Smith, also the developer Patrick, and the researchers Julia and Andressa. Next. We created a lunar cable car system building on the last year's projects. This slide shows the visual differences between this year's version and the last year's. Next. We made some improvements in this year's edition. We gave the cable car an increased capacity. Now the cable car can transport up to 4 astronauts simultaneously with a smoother movement. And we made new interactions. We focus on collaborations with other teams such as Brunel and Florida Polytechnic University. Next. Now about the cable car. The cable car consists of a network of cable cars with a lifting platform that allows astronauts to travel between bases and transport cargo. This year's biggest improvements were in the cable car visuals and the movement in the simulation and interactions. We added a power source interaction, so the cable car can receive energy from the greenhouse, the Florida University greenhouse. Also, some communication interactions. Now the cable car receives data about the Brunel's lander arrival. And the movement still loop between all the stations and supports up to 4 astronauts. The data elements are position, orientation, mass capability, battery level, travel time, and velocity. Interactions with the astronaut and the cable car station, and tools used was Blender for modeling, Substance for textures, and Java for code. Next. The other federate we made was the astronaut. The cable car only makes sense if you have someone to use the cable car, so we made the astronaut. After disembarking the lander, the astronauts can travel using the cable car system and proceed to the greenhouse. The data elements are position, orientation, and mass, interactions with the cable car and the lunar space, and tools, just as the same as the cable car, was Blender for modeling, Substance for textures, and Java for code. Next, please. The challenges we faced this year. The first one was code complexity, because we have to manage multiple astronauts, and this made our code base grow quickly, which became a problem to organize, and also managing a high number of objects in different threads caused concurrency problems. So we had to learn how to synchronize and access the data. We had some team changes in this year. The modeling department have some members that graduated in FACEN, so we lost some valuable members, but the team worked hard to fulfill their absence. And the last challenge was co-developing the project in close collaboration with other teams. We solved this by holding some weekly meetings with Brunel and Florida to get everything working. Next. And the lessons learned. The first one was the importance of following the schedule to ensure the project progress efficiently. We did to strengthen the relationship with the other teams so the interactions can work. And this year we gained a deeper understanding of HLA and RTI alongside spacephone. Next. Those are our final 3D models for the cable car system. Next. And when you put all together with our interactions, we get this big system with the lander, and I don't see the greenhouse from here, but yes. Next. And thank you, everyone.
Thank you, Paige.
All right, thank you very much, Fastens. Next, we are going to have Florida Polytechnic University.
Okay, thank you. Welcome everyone to the space exploration event. We are the Aeroponics Lunar Greenhouse Garden Federation, and we are from Florida Polytechnic University. Next. My name is Sarah Barlow. I'm the communication lead, and this is my amazing team. Anand Dewansing, he's our design lead. Bradley Larson, our documentation and implementation lead. Adriana Bottega, our
Project Manager and Quality and Assurance Lead, Natasha Gatas, Research and Implementation Lead, Jason Rodriguez, our Technical Lead, and Landon Johnson, our Implementation Lead. So this is our baseball card, our data elements, or essentially our scope. We were looking for biofuel energy output so that we can give energy to Fasens, and irrigation monitoring to give enough water and nutrients to the plants. Our interactions was Fasens Cable Car and Fasens Astronaut, and I just want to say thank you so much to Kaiki for all of his help and assistance. He was amazing. And then our tools that we used was Unity to construct the greenhouse. We also used Dawn and Pitch RTI, and then Blender to create the smaller elements of the greenhouse. Next. Some of the challenges that we faced was limiting our scope. We wanted to tackle everything that could possibly exist underneath the greenhouse, but we had to limit our scope to only the irrigation monitoring and the production of electricity using a Rankine cycle. So you turn biomass, burn it, the water turns into steam, which turns a turbine, producing electricity. The hurricanes, because we're from Florida, so we were hit a little hard by Hurricane Milton, and it caused a delay in our progress. And also, we had to adjust to new software such as HLA and Dawn. Some of the lessons that we learned in our project was time management. So staying on schedule requires realistic deadlines and consistent follow-through. Also, clear communication is crucial. So regular updates and transparent dialogue help prevent misunderstandings. And also documentation, making sure we are up to date with our records is very important. And just a more thorough description of our greenhouse garden is an aeroponic greenhouse garden that will be simulated to provide a sustainable method of harvesting food and oxygen to provide nutrients, biofuel, and atmosphere for the lunar base. Specifically, we'll be investigating water and plant resource management in consideration of the limited resources of the moon. And so our behavior is oxygen, food, and biofuel production. And this is a little demo from the astronaut's perspective, going through the stairs, interacting with the doors. As you can see, when one door closes, the other one opens. And then this is our model for the irrigation system. So there's a water tank that provides the nutrients and water to all the plants. And then back here is our Rankine cycle, which generates the electricity. Next. And lastly, this is a sped up time lapse of the plants growing in the greenhouse garden. This shows that the irrigation system is working and running, and every irrigation cycle should have the same amount of nutrients per cycle. In just 1 second, we'll be able to see the cabbage bloom. Any second now. There he goes. Next. So thank you. This has been an amazing opportunity, and we're very grateful to participate.
Excellent. Thank you very much, Florida Polytechnic. Next, we're going to have Genoa.
Okay, can you hear me?
Yes. One moment. Screen's got after end. All right. I should see your slides and I can hear you.
Yes, can see. Okay, thank you. Okay, good morning and good afternoon, everyone. My name is Farshad from University of Genoa in Italy. My colleagues, Luca, Giulia, Filippo, and I are member of the simulation team, research group at University of Genoa. Also, with collaboration with Staticus student, Francesco, Saba, Fatima, Luca, and Giorgia, which is an international master program that represent a new discipline of strategic engineering, which combine modeling, simulation, artificial intelligence, intelligent agent to support decision maker. Today, we are excited to present our model for C 2025 under supervision of Professor Agostino Bolzano. Next slide, please. Okay, here, this is our baseball card. This year, we work on simulating a constellation similar to GPS for Earth. We use four satellites, which is minimum number of satellite to determine a 3D position. The orbit is very similar to Lunar Gateway, and the application can be support precise landing, determine 3D position, surface mobility, and South Pole exploration mission. As long as lunar habitat grow and more exploration happen in the moon, the need for our system will also increase. Next slide, please. Okay, about orbital dynamic, as I said, the orbit would be similar to NASA Lunar Gateway because it's an optimal orbit to ensure maximum visibility over the South Pole. The other characteristics would be it's highly eccentric and also highly elliptical. The closest point to the moon would be 3,000 kilometers on North Pole, and the farthest would be 70,000 kilometers. And the orbital period is almost 7 days. The techniques, the numeric techniques we use is Ongecuta to solve orbit differential equation. Next slide, please. Okay. The project is challenging because it requires several tools to connect together, such as PyRTI, program language like Java, Eclipse, IDE, also 3D design software like Unity, Blender, and done. Next slide, please. Lesson learned. So the main lesson is simulation design and concept, HLA context and logics, interoperability, and interaction between simulations, and importance of the time management in federation, how time advances and works, orbital mechanics, implementation, 3D modeling, done. Also, importance of the competition and collaboration. While competitions push teams to perform their best, collaborations allow us to enhance and exchange ideas, solve problems together, and grow as a community. Next slide, please. Future work would be having more interaction between other feathers and teams, using more attributes and data to publish. This year we use position and velocity, and if we want to extend our model, the attitude of the satellite would be the next option. Also, we like to implement our code instead of using HLA starter kit because it's somehow like a black box and it is hard to see what happened behind the scene. Test trick and trick HLA would be next option for us. Next slide, please. Thank you for attention. That was our presentation.
Excellent. Thank you very much. Okay, the next team is going to be IMT Minds.
Yes, hello everyone.
Hello. One moment.
All right. So again, hello everyone. So we're the team from EMT Minares. Can you go to the next slide page, please? Thanks. So our team members are a group of undergraduate students who are finishing up their bachelor's. And well, they are Wendy Dijoux, Julien Mougin, Alexandre Gauthier, with the supervision team being Gregory Zakharowicz and myself, Leonardo Dodau. So everyone of them basically worked the same roles, since we have, as we will see in a bit, 3 federates. So there was a lot to do and not enough members. Can you go to the next slide, please, Paige? So the first federate that we worked on was the waste storage system, and it's designed to basically hold multiple types of goods, such as materials. It could be steel ingots, iron, and such. It can hold as well waste bars, so stuff that need to be repaired or decomposed, and such, as well as parts that are recycled. No, so we will see the interaction as well later on, but we basically build an interaction matrix between our own federates and UCF's team, as well as Catholic University's team. Can you go to the next page as well, please? So the next federate that we implemented was the waste transformation system. So this federate's job was to take materials from the storage system and then either transform them into, well, something else. So basically recycle them or just decompose them and get whatever material we can from it. So its main interaction was with the storage system. And we will see the details in a bit. Can you please go to the next one? And the last federate our team implemented is the waste pyrolysis system. So this one is based on the fact that, well, we're on the moon and we can harness solar rays to create a type of oven to basically just perform pyrolysis on waste items that we don't have, since we don't really have a lot of oxygen. So we try to substitute that with well, reflective plates that will basically burn whatever waste we have to get CO2 and water mainly. Can you go to the next one, please, Paige? So this is our interaction matrix. So as I said, we interacted internally between the federates that we created. So between publishing and subscribing the materials that we have, the pyrolysis residuals that we have, and the decomposition or recycling that took place. Our interaction with Lars, which is one of the federates of UCF, was to basically publish whatever materials, parts, and basically waste we currently have in our storage, and subscribe to any request we get from Lars to perform pyrolysis, decomposition, or recycling some part to obtain a new one. The final interaction was with the ERRV, which is Catholic University federate. So that one is to publish information about the collected material. There was another interaction that was added later on, which is to receive parts that they collect, or basically damaged parts that they collect, so we can store them, transform them, or basically perform pyrolysis on them. Next one, please, Paige. For the challenges faced, well, most of our team, so the students are French, so it is in English, so that was a bit of a challenge, but they did okay in the end. And there was the aspect of interaction with students all around the world. And this was their first experience in distributed simulation, as well as HLA standards, which they were able to overcome. And there was a lot of new software to discover and manipulate. Can you, especially Pitch and Blender. Can you go to the next one, please, Paige? And as for the lessons learned, well, we gained some knowledge in space exploration, so new skills in UCAD software as well. Their programming skills in Java, well, they had them, but they were improved with the new type of functions and ideas that were there. The knowledge, there was some new knowledge gained regarding speed simulation and the HLA standard, and they realized that, well, teamwork makes the dream work, we can say. So teamwork is key. Can you go to next slide, please? And this is just a snippet, so just a picture, which we will see later on in action. So of the three federates working, so we have the storage, which are like the rods that you can see, the pyrolysis, which is down with the oven, and the last part, which is to the right, is the transformation system. So we see that in action later on. Can you go to the next slide, please, Paige? And that was it from us. So thank you for your attention, and hopefully we see you in the next one. So this was it from us.
Excellent. Thank you very much. The next team will be the Lille Catholic University.
Yes, hello, Paige.
Hello.
Can you hear me?
Yes.
Perfect. So before starting, I would like to thank every single person who offered us this opportunity. Hello, everyone. Today, we are excited to present you our Federate, the Emergency Response Recovery Vehicle, or ERRV for short. First, I will explain the project idea, then how the system works, the tools and technologies that we used, some challenges that we faced, and finally, what we learned from this experience. Next, please. So here is our team, Hussam, Wael, Joe, and me, Mohammed. We are students from the Catholic University of Lille in the École du Numérique. Michel and Antoine are PhD students. Next, please. So our federate rule is to retrieve machines or members that are damaged in high-risk areas. That's why we built a simulation that takes place on the surface of the moon where there are many risks like difficult terrain, for example. To develop this project, we use tools like Unity for the 3D environment, Blender and Dawn for modeling, and Pitch RTA for communication between systems. We also use Java and C# for the developments. Next, please. Yes, so here is how ERRV works. First of all, it received a distress signal, which included two informations, the location and the weight of the object or person to recover. Once arrived at the destination, ERRV will evaluate the object. If everything is okay, it goes to pick up the object or person, then deliver it to the appropriate base. After the mission, it returned to stand-up mode and recharge, and it is ready for the next mission. Next, please. So here is our 3D model. To do the operation, the system follows certain rules. For example, it has a maximum weight limit for what it can carry to guarantee safe movement on the surface of the moon. It can also interact with other linear facilities to deliver the appropriate object. For example, humans to residential quarters. And in this project, it worked with the system built by IMT team, the waste storage system. Next, please. So yes, we also faced a few interesting challenges. First, doing the simulation for the surface of the moon was really complex. Then, learning how to use tools like Unity, Blender, and PitchRTI was a big step for us. And finally, setting up interaction with other federates was harder than what we expected. Sorry. Next, please. Despite these difficulties faced, we learned a few nice things. We discovered how space environment simulation work. We learned about distributed system using HLA and how to use multiple tools and software such as Pitch RTI. Finally, we learned the value of teamwork, sharing tasks, and combining different skills sets to build working simulation. Next, please. So thank you to listening. Very happy to do this project with my team. And if you have any question, we are here to respond to you. Thank you.
Excellent. Thank you very much. The next team we're going to have is the National Technical University of Athens. However, because they're on a university holiday this week, they sent in a video recording that I will share with you. So let me know if anyone cannot hear the sound once it starts.
It's a great pleasure presenting at SE 2025 our conceptual work in situ lunar-based data stream processing for telecardiology services in space. I'm Panagiotis Michael, and I represent the National Technical University of Athens and the Karokopion University of Athens in Greece. Our concept builds on the work of the previous year for SE, where we have proposed cloud services for the support of humans living on the moon, and we have identified a suite of infrastructures required for such a deployment. These services are deployed through an extension of the Internet of Things, which we have named the Internet of Space. In order to provide such services, we have envisioned the equivalent to an airport facility on Earth, which we have called a lunar port. As a core element for the construction of the lunar port facility, we have used existing realistic paradigms, such as the NASA Habitat Demonstration Unit, as presented in SE presentation, How to Play Nice Across Time and Space. Based on this core HDU element, we have proposed a modular, scalable lunar port facility, and in this slide, with the use of a grid of HDUs, we have modeled the Frankfurt Airport Terminal 3 on the moon. Within such an HDU, we have hosted a high-performance space data center performing in situ data stream processing in order to support a large number of humans and vehicles, monitoring and coordinating operations, and sustaining life in real time. We perform data stream processing based on the technology developed by our team, initially at the UCLA Hoffman cluster, and later on at the ARIS high-performance computing infrastructure of Greece, GRNet. Our technology is capable to monitor approximately 500 million Internet of Things in real time with a latency on the order of milliseconds. This year, our main goal is to provide telemedicine health services to astronauts and humans living and working on the moon surface, and especially to provide telecardiology services. More specifically, we propose a lunar port cardiac intensive care unit consisting of a control tower, a cardiac center habitat with a cardiac intensive care unit, data center facilities, and terminal services for human support. The cardiac intensive care unit will be providing telecardiology services to humans, living inhabitants, and to astronauts on missions, and health monitoring through large-scale electrocardiogram systems in the form of Internet of Space devices. Electrocardiogram signals will be transmitted through the Internet of Space to a cardiac intensive care unit. Doctor teams, supported by real-time analysis of ECGs generated by state-of-the-art artificial intelligence algorithms, can monitor and diagnose cardiac issues and proactively guide operations teams to rescue humans at risk. This concludes my presentation, and I would like to thank you and wish best of success to all participants and the coordinators of this final SE 2025 event.
All right, I know they're not allowed to hear me, but thank you, Athens. The next university will be the Naval Academy of Bulgaria.
Hello. May I ask for permission to present our presentation ourselves, please?
Sure, go ahead.
Thank you. Do you see it?
Yes, I can see it.
Thank you.
Hello, everyone. We represent the Naval Academy of Bulgaria. My name is Stefka.
I am Simeon.
And this is our project, Litos.
These are our team members, and we would like to thank our mentors, Professor Radeva, Professor Nikova, and Dr. Andreev.
This slide showcases our main federates: a base, a resource extraction and manufacturing facility, a suspended lift line network, a regulated gathering and transport vehicle, a heavy resource export shuttle, and manned transport rover.
This is our postcard. It represents our base, and it has different parts like living quarters and biosphere, a logistics center, a scientific research laboratories, and storage hangars.
Our main mission is to establish a sustainable and efficient operational framework for lunar and deep space exploration.
And our first federate is our base. As our mission offers a strategic and resource-efficient approach to establishing a self-sufficient infrastructure on the moon with long-term goals extending to Mars, by focusing on in-situ resource utilization and advanced manufacturing, we aim to significantly reduce the need for costly and complex material transport from Earth.
Our next federate is the Resource Extraction and Manufacturing Facility. This is supposed to be a stationary lunar federate designed to support in-situ resource utilization. Its main functions include extraction and refining of metals and minerals, a production of high-purity silicon and iron-nickel alloys, a glass fabrication for habitat windows, visitors, and photovoltaic applications, a metal panel manufacturing, and aerogel synthesis.
Our third federate is our reflector solar farm. And unlike the conventional solar panels, we propose using solar reflectors to reflect sunlight and heat water, which is easier, and the reflectors are easier to manufacture with local materials, and it's cost effective. They will generate power for lunar operations and be adaptable for Martian deployment, offering a flexible, scalable energy solution.
The next federate is the suspended lift line network. This model showcases a modular transport infrastructure designed for efficient, fuel-free material transfer across the lunar surface. Its key features are suspended cable network, automated cargo gondolas, electromagnetic and solar-powered propulsion, and scalable architecture.
This is our heavy resource export shuttle. The model represents a high-capacity transport system engineered to deliver the essential infrastructure and materials from the moon to Mars. Its capabilities include a high-capacity cargo bay, a support for pressurized and unpressurized cargo, and its lunar-derived fuel system reduces the cost and dependency on Earth-based propellants.
Our next federate is the regulated gathering and transport vehicle. It acquires and transports storage capacity and fuel between stationary and dynamic nodes. Its main functions include integrated excavation system, high load capacity, modular storage compartments, and autonomous and remote operation.
And our final federate is our manned transport rover. It's a versatile mobile platform designed to support extended missions across the challenging extraterrestrial terrain. Its features include a life support front module and an expandable rear cargo module. It's also capable of towing supply trailers, habitat modules, or mobile power stations to support mission logistics.
Thank you for your attention and this opportunity.
Excellent, thank you. Did your team also have a video? I believe you said you wanted to share.
That's not us. I don't think so.
No, I don't think so.
Yeah.
All right. Thank you. All right. Thank you for your presentation. We're going to move on to UCF, so it's the University of Central Florida. So they have a few distinct teams as well as functions that they did foresee. So we're going to start with their federate design presentation.
Hello, hello. Can you hear me?
Yes, I can hear you.
Oh, yeah. So obviously, as Paige mentioned, we are the University of Central Florida, the infrastructure team, which is also the modeling team. Our team members are Tristan Nelson, Dylan Mu Hernandez, Manaf Nasir, Lucas Durimer, and me, Maddie Furhat. Next page, please. So we made two federates this time around. The first one is Lars, which is akin to TARS from the movie Interstellar, and he serves a similar functionality as a lunar assistant. Lars will transmit data as well as show data for anyone on the lunar surface. He can speak to other federates, as Dylan will document or show in the interaction matrix. He is a sort of rover that you'll see in a moment that walks on treads. We decided to go with a different kind of movement than TARS from Interstellar because it seemed a bit out there. But yeah, he provides interactive responses, simulates data, simulates information, and then can transmit that data and information to other federates or other pieces of technology on the lunar surface. Next slide, please. Our second federate is the landing beacon, and it's fairly self-explanatory. It is a small static tower that can transmit data to landers, beacons, rovers. It can help them adjust their trajectory. It can give them idea of the state of the lunar surface. It can detect and serve as a kind of, obviously, beacon. It has lights around the base that you'll see in our actual model that can be seen from ways away. And yeah, if you'd like to go to the next.
Right, can you guys hear me?
Yes, I can hear you.
Okay. Hey, everyone. I'm Dylan. I'm also part of the UCF infrastructure team, and my work focused on federal development. So the figure that you see on the screen is our updated interaction matrix, which basically gives us a high-level overview of how our custom federates communicate. So each cell shows a publish and subscribe interaction between two federates. And on the right side, you can see that we have federates that were created by the Brunel University in London, as well as EMT in Paris. As you can see, we have both internal interactions as well as external interactions. Now I'm going to explain the interactions in more detail in the next slides. Right. This is our Lars rover. As we mentioned earlier, Lars sends environmental reports, specifically to both the waste storage system and the landing beacon in a clean and readable format. And it also asks EMT's waste storage system for inventory updates, and it gets back organized list of materials, parts, waste, or more. And on the right, you can see a picture of our large 3D model designed in Blender. Next slide, please. Now this is our landing beacon. This federate acts as the monitoring unit for incoming landers and spacecraft. As for its interactions, it first tracks Brunel's lander's position and notifies the spaceport once it gets close to the landing site. It also receives status updates from Lars and sends back messages. Overall, it plays a key role in coordinating safe landings and communication between federates. As you can see on the right, we have our 3D model for our beacon, also designed in Blender. Next slide, please. Okay, to wrap up my section, these are some of our successes and challenges we encountered along the way. First, we were able to successfully connect both Lars and the landing beacon to the RTI and complete full interaction cycles, even with external federates. We also had very smooth collaboration with international teams, which made testing and debugging a lot easier. I wanted to give a quick shout out to Maziar, Kaike, and Leonard for being part of this journey. Now for our challenges, some problems we faced include alignment with XML files and phone modules. There were times where federates were not showing in the web viewer, which took a lot of debugging, and despite those, we made solid progress and get things moving. Next slide.
And finally, for our progress and plans, currently we have created 3D models in Blender, as well as obviously created main classes to instantiate the federate. We have interaction logic, as Dylan mentioned, with IMT Minds, with Brunel. And we have Dawn visualization all but completed, but as for future additions and add-ons, whether it be for future UCF teams or even us in future iterations of the C event, we'd love to have even more complex interactions with even more teams, as well as full federate movement and implementation in Dawn, so that we can see our Lars rover, as well as the landing beacon within the observer network, as well as just creating more federates. So that was our presentation for our models and federates, and Tristan will be speaking a bit more about the server infrastructure.
All right, so I'm going to make this short and sweet for you guys. My name is Tristan Nelson, obviously, as Monty mentioned. I work specifically on the infrastructure, mainly the server. But I kind of wanted to give you guys just a brief summation and a quick walkthrough on how the server actually worked, how the implementation was, etc. Paige, can you go to the next slide? Oh, there we go. Okay, so the infrastructure in the server itself, I just wanted to give you guys an overview. I'm not going to go too complex into it, but basically we hosted on an Amazon AWS EC2 using their services at Amazon's. We decided to use a T3 small, not a T3 medium, but we were debating going and switching over before we ran into some issues yesterday. But regardless, we used a T3 medium, just think of it as a T3 medium, and the operating system was a Red Hat Linux OS, which is basically just Linux, but designed specifically for EC2 integration. We were messing around with stuff like CloudWatch, which is basically just an Amazon integrated feature that allows us to kind of go through and see like usage rates and stuff on the server, but we're kind of blocked from that. Go into a little more detail, maybe. We'll see. In terms of the EBS, the Elastic Block Storage, that was an idea that we had broached to Paige, and we may still implement it maybe after next week, but right now, I don't think we're going to actually require that, at least for what we're thinking for the rest of the future of the server and future of C in general. In terms of the server itself, obviously there's two core functionality. There's the WireGuard VPN, which you guys use to connect, and then appear local on the server so you can directly connect to the CRC, as many of you have done. That connection was actually fairly simple. I would say the hardest part was just messing with firewalls in Amazon AWS. I blew up a couple of servers, I'll admit it. But I didn't for the server that you guys are using, which was beautiful. The firewalls themselves were fairly simple after you kind of get a feel for them, just making sure that, only certain people can connect to certain ports, and, that kind of stuff is fairly important, especially since you guys are directly connecting, right? We need to make sure no one messes with the server. In terms of the other part, the more important part for this specific presentation and for C in general, the HLA creation and permanence. So Obviously, everyone here requested a pitch license. I did the same. Basically, what I did was requested the same licenses and then moved that over into the Amazon server, nothing complex. Other than that, we had core federates, same core federates. Actually, I don't know how many people created their own CRC or their LRC with all the core federates inside, but basically it's just an Eclipse, just an adaptation. You move that stuff over into Eclipse and then you launch it. In my case, all I did was exported some of the core federates into basically runnable jar files, which you can actually do. It's like an integrated function of Eclipse, which is awesome. I did not want to spend 10 hours trying to figure out how to do that myself. So it's beautiful that it was fairly functional in terms of just moving this stuff over, making sure that the XML files and everything else was there to make it run properly. Can you go to the next slide page? Okay, so I kind of mentioned all that stuff. I wanted to go a little bit more in depth on the core federates. So the core federates make up the C Federation, as we all know. Those include the Space Master, the Space Reference Frame Publisher, and HLAted-on. The Space Master is something that I was given to by Pitch. I requested it. They sent it to me. It's just a shell script, so I was able to just run it, and it works like that. The other two, not so much. Space Reference Frame Publisher, I believe, is a NASA product, as I know the HLAted-on is. I don't know for the Space Reference Frame Master, Space Reference Frame Publisher specifically, but basically the process that I described before is what we did. I downloaded them, ran them through Eclipse, made sure that they were functioning, and then I exported them as headless jar files so that, a part of it that I didn't mention is that we only have a limited amount of credits on the for the server. About $1,000 worth. So I had to make sure that I'm not eating up a ton of CPU and GPU usage rate just to run like Eclipse, which is a fairly complex program. Can you go to the next slide page? In terms of the successes and challenges, just go through it really quickly. I mentioned the server detonation as a challenge and the firewall struggles. That was very annoying early on. I've never done any of this stuff, so this was kind of a fun experience. We did have, as all of you did, some delays. A lot of it was just waiting for Pitch. Pitch is a fairly busy company. I understand the struggles and time-consuming process of going through and individually sending each license. I'm sure it's quite annoying. So, but that was an issue for us. Is we were able to implement stuff fairly quickly, but it's when we got it is when we were able to implement it. Past that, there was a lack of instruction. Like there's not really like a go-to on online of like, okay, this is how you put an RTI into an AWS system. So that was a kind of fun process. Past that, obviously we worked well together. We communicated. I think the simplicity itself, all of these jar files and stuff already exist on the web. On the GitHub mainly, actually, but still, they already exist, so I was able to just pull that and then implement it into the server, so it's a fairly smooth process once you kind of figured out how to do it, which is great. Next slide page. In terms of the website, which some of you guys have used, some of you guys didn't have to since I manually added you into the WireGuard server file thing, but we have a server that we've created, and the idea is for future UCF infrastructure teams for future events, that this will automate the process. So anyone like Paige, who is obviously the technical chair of this event, anyone like Paige doesn't really have to touch it. Like she can just kind of leave it. Obviously Paige and everyone else is fairly busy, so we wanted to make sure that this process was fairly automated. Because the higher the automation, the less hands-on stuff that you have to do, and hopefully that means that the future infrastructure teams can focus on other things, maybe more federate development, more implementation, just stuff like that. That was the goal, and I think that we're fairly close. I don't know if we hit it on the head, but we tried. But anyways, that's it for the infrastructure. If you guys have any questions, let me know. But I just wanted to give you like a brief rundown of how it all worked.
Excellent. Thank you very much. And our last presentation is going to be from the UCF Dawn team.
Yes.
I think
Hello,
they're
Paige, can you hear me?
demo. Yes, I can hear you.
I'm going to share my screen. I'm actually going to do a short presentation as well before the demo. So we're Dawn 4.4. For those of you who don't know, Dawn 4 is the Unreal Engine iteration of Dawn 3, which is still in development. As far as our team, my name is Luis. I was our project manager and I worked on the back end. We have Trey, who also worked on the back end with me, Megan, who worked on the UI, Ethan, who worked on the back end, and Paige, who also worked on the UI. And our sponsor was Mike Conroy from the Florida Space Institute. So what was our goals for our iteration of Dawn? So we were to prepare Dawn for the CE event. What this entailed was implementing the new network stream simulation feature, which would allow you to play back simulation data coming in from a network stream from HLA to Dawn, and also record that data into a file so you can play it back later. We also made some updates to the UI and the user experience, and we implemented MPC2 playback as the previous version was using MPC3. As far as the network stream works, basically, if you don't know how the HLA to MPC federate works, basically takes the HLA simulation data and converts it to MPC, which is an XML formatted simulation data type that Dawn reads in to playback simulations. So this creates a that streams this over. And on the side of Dawn, what we do is create a new thread separate from the game thread, connect to that socket using the IP address and port that the user puts in. As far as how the data is received and recorded, the data comes in not always in a full time tag, so that's why we created a accumulated buffer, which waits until we have a full XML tag. When we receive this, we pass this on to the media controller, as well as to a recording file, to the XML file, so we can have it for later. As far as how the simulation playback works, for those of you who are familiar with Dawn 3, it is quite similar. In our simulation directory, we have a models folder which contains a metadata.txt file. And this file will allow us to load in the static models who have a predefined position as well as their relationships. We also, a big thing for us was implementing correct parent relationships with the models. So, you know, for example, some models may be fixed to the moon's surface, and we believe that in the previous Dawn, they were calculating the position relevant to this, but with Unreal Engine 5, we're able to establish parent-child relationships, so everything moves relative to their parent. We also added interpolation since the data coming over the stream is in 1 second intervals. As you can imagine, if you play over 1 second intervals in a 3D viewer, it becomes quite choppy. So we added interpolation to smooth this out. We also made a script that allows us to create demo simulations, and also a script that allows us to stream simulations so we can mock the server, so we didn't have to so I didn't have to keep messaging Tristan on Discord every single day asking him to put the server up so we can test our new feature. Also, we added a snap to surface feature, which basically allows you to define ground objects and have them always stay attached to the surface that they belong to. As far as the UI, there were some problems with consistency as well as being able to view it. As you can see before, sometimes the rotating space station in the main menu would not allow you to read some of the buttons. So we fixed that. We also added some sound effects, some hover features. We also added some new widgets like the network simulation page and the ping system, which we will get all into in the demo, which I will begin now. So I'm going to open up Dawn right here. So let's start off all the different features. Here we have the settings. You can adjust, obviously, your visual settings. We have a new import model option that we added. The reason we did this is that if you're going to join a network stream, perhaps you don't want to load in your models while you're joining the stream. So this allows you to pre-import the models into the engine. And here in the network stream simulation, you can see we put in a network address, which in this case will be localhost, as I am hosting a mock of the server, sending over a simulation that we created. Here you're going to select the directory. This will be the simulation directory that contains your config file. And here you select the recording directory, which will be where the recorded XML file will be sent. You can see this here will be the name of the file. And also you have the option to import models, or you can uncheck this if you've already imported your models beforehand. But then we'll hit connect and we'll go into the simulation. As you can see, all the data is being taken in very fast because we just have the stream send it all in instantly for the purposes of the demo. But this is a simulation that we created. As you can see, on the right side, we have the general simulation data, and we have an inspect panel, which actually defines the position of all the objects. On the left, a new feature that we also added is the ping system. So for example, we can see the lunar shuttle in the middle over here. If we click here, we'll have a ping that tells us our distance relative to it.
Sorry to interrupt, but I don't know if it's frozen for anyone else, but it's frozen for us here.
It's frozen? Is it good now?
Yeah,
Yep, there it goes.
super far behind.
We got it now.
It's good now?
Yes.
Oh, God, how much did you guys miss?
So we went not much.
Okay.
Keep going.
Not so much.
So yeah, so now you can see there's a ping that displays objects across the screen. For example, we can turn on the astronaut, the moon port, and you can actually hover over and teleport to these pings. So I'm gonna play back now. So this simulation is actually each telemetry is 1 second time step, but since we add interpolation, it smooths out. You can see at around 10 seconds, we'll see some astronauts start to come out of the base.
Luis, it's frozen again. You might want to just play the video we recorded.
Is it good now?
It keeps refreshing when you do that. Oh, no, where it's playing now.
Interesting. Okay.
I think it's frozen
Is it
whenever
good now?
you're capturing your. No, I think it's frozen whenever you're capturing your mouse and stuff.
Okay, it's frozen right now?
We saw the astronauts come out of the habitat.
Okay. So if you teleport to an object, can you guys see it moving right now?
Nope, you're still frozen.
And I think your webcam is too. It might just be the internet.
Yeah. Okay, is it good now?
Kinda.
Okay, Luis, if you want to try, go ahead and turn your camera off.
Yeah, let's see that. How is it now? It seems as though whenever I click into it, Zoom just Teams just stops sharing. Actually, let me try sharing the application window instead of my screen. All right. Can you guys see me moving now?
No, it's still frozen.
No, it's okay. I mean, we saw some of the movement.
Yeah, we saw the movement. We could see now the numbers on the screen with the service.
Okay, I'm sorry about that. There's a lot more we wanted to show you guys, but if it's gonna work out like that, then so I'm gonna end it
Whatever
here.
you did, it just caught up and you're at 108 seconds. I was progressing, the time just stopped.
Okay, can you see it now?
We're at 111 seconds.
If there's a minute clip you want to show from any of your the videos you recorded, otherwise we did get to see a little bit of it, and it does look very impressive.
Okay. Let me see if I can pull up the video from our demo.
Yeah, we did a video for our showcase that'll have Ethan talking over it, but you guys could at least see it better.
Yep. Go ahead. You guys probably have about a minute still if you want to go and show it.
Yeah, pulling it up right now. Okay.
Were you intending to play the audio, Luis? It's muted right now.
Oh my
If you want to
word.
talk over it, just go ahead and
Yeah.
talk over it.
So,
We can see the
yeah.
video playing.
He's just showing the ping system now. Now he teleported to the object. And one of the things we added actually is when you teleport to an object, you attach to it, similar how the parent relationships are established with the objects. So when the lunar shuttle starts moving, your character will actually move with it. And here you can see the astronauts going into the shuttle. And I'll just skip over a bit for the sake of time. You can see we follow the shuttle as it moves. And on the right in the inspect panel, you can see its position change live. And yeah, for the sake of time, I'm gonna end it here. But yeah, I'm sorry about that, guys. I don't know what happened.
No problem. We got to see a lot of the features, and I'm very much looking forward to upgrading to that Dawn next year.
Sounds
It
good. Thank
looks
you.
absolutely grand. Absolutely grand.
All right, thank you so much for our teams. That is the end of the team presentations. And as I think a few of them have mentioned, they've been working across time zones, across languages, across oceans. So this is a really cool feat. So to show off a bit more of this international collaboration, we're going to move into our Federation execution part of the presentation. So I'm going to go ahead and ask the UCF infrastructure team to please share their screen. So UCF was in charge of setting up the server, as you guys saw, and running the core federates, which is our execution control, the pacing for the time, as well as the reference frame publisher. So if you could switch over to our lollipop view, please. All right, so at this point we have the core federates up, which means time is advancing. But now we're going to go ahead and add each of our active teams that have created federates to join our federation. So I'll call you one at a time. So Brunel University, would you like to join your federates?
Sure, Paige. The lander is joining now. Brunel has 2 federates, lander and spaceport. Lander looks good. Joining the spaceport. All good on our side.
Perfect. Fastens, would you like to join your federates? Kaike, looks like you're trying to speak, but I do not hear you.
Hi, thanks, Paige. Sorry for that. So we will join our federates now. We also have 2 federates, the lunar cable car and the astronaut. So the first one, let's connect with the lunar cable car. Okay, all good. And now I will connect with the astronaut federate. And all good too. Thank you, Paige.
Excellent. Thank you very much. Florida Polytechnic, would you like to join your federate?
Sure, one moment. Give me just a few seconds. I need to disable my firewall. All good. We're connected.
Excellent. Genoa, would you like to join your federates?
Yes. General team has 4 setter. Okay. Okay, I'll join.
Excellent. Thank you. IMT Minds, would you like to join?
Yes, of course. So we're launching our storage system. All right, now launching the transformation system. Okay, all's good. And lastly, launching the pyrolysis system. All right, all three federates are up and running.
Excellent. Little Catholic University, would you like to join?
Yes, sure. Okay, perfect.
Thank you. And UCF, would you like to join?
Sure. I'm going to start with Lars. Okay. And then our landing beacon. All right, all federates are running and no issues on my end.
Excellent. At this time, are there any other teams that would like to join that I have not already called? All right, that is all the teams that we have joining. Congratulations, everyone. That is a successful Federation execution, and that is a huge accomplishment. Distributed simulations is no small task, and it requires a lot of international collaboration, so congratulations. All right, at this time, we're going to go through the teams that have joined our Federation here, and we're going to let them share what it is their federates and their simulations are currently doing. So first, we're going to have Brunel Fastens and Florida Polytechnic will be presenting theirs together.
Thank you, Paige. Hello, everyone. I'm Kaique from Fastens team. I'm really happy to be here today and to present our visual demo running over Dawn. I'll start by sharing my screen. 1 second. And let me know if you can see things moving inside Dawn.
Yes, I can see it.
Nice. So I'll start by sharing my screen, and then now I'll hand it over to Maziar from Brunel University, who will walk us through the initial steps of our mission. So I will ask Maziar, could you please start the lander and go ahead with your presentation?
Thanks, Kike. Yes, we are actually, as we mentioned in the presentation, Brunel contributed 2 federates, the spaceport and the landers. For both federates, both federates are physical entities, meaning that they are actually 3D models presenting in Dawn. And our visualization platform, for the lander design, we closely followed Artemis' vision for future space vehicles, and for the spaceport, a blueprint from Space Design and Moon by Alex Anderson and his team. In this, what we are showcasing today is 4 teams collaboration: UCF, Brunel, Fastens, Florida Polytechnic University. So what we are showing now is the lander starting descent towards the spaceport, and on successful landing, the spaceport would receive a confirmation and will send a message to the cable car that the lander has touched down. Kai, whenever you're ready, I run the lander.
We're ready. You can go ahead.
Right. The lander is running now. Lander approaching the spaceport. Now we hand over the simulation to Fastens, taking this opportunity to thank everyone from SISO, C team, and also UCF Fastens, especially Kai, Dylan, and Tristan, and everyone else. Thank you very much for the opportunity. I hand over the simulation to Kai.
Thank you, Maziar. So now let's just wait a little until the lander reaches the spaceport, and then I will ask you, Maziar, to send us the message that the lander arrived, okay?
Sure, yes.
Okay. And also, just to mention, this is the UCF beacon. We put it here in Dawn, just so that we can have all of our visuals together, and the lander is being recognized by the beacon, as Maziar explained. So let's just wait a little more for it to reach the ground. It reached.
So at this point, we have spaceport has received the confirmation lander has reached the platform. Now I am sending the confirmation to Fastens cable car. Message sent.
Did you receive the acknowledgement?
Acknowledgement received.
Okay, so let's wait. So as you can see, the astronaut safely landed, and now it is going in the direction of the lunar cable car system. So let's follow its path. Great, now it reached the station location and it's waiting for the cable car to arrive. But for now, let's shift our view to the cable car. For this year's presentation, we set up a robust demo to showcase the lunar cable car system. We are simulating 8 astronauts at the same time. So let me focus on the cable car. So we are simulating 8 astronauts traveling simultaneously, each heading to a randomly selected station. This really demonstrates the system's improvement and capacity. The cable car can now accommodate up to 4 astronauts at once. So let's see how that plays out. The cable car is just reaching the station where the Brunel astronaut was waiting, and now some astronauts were invited to join. They are each assigned to a different seat inside the cable car. So let's follow the Brunel astronaut's path to see where it goes. I think it's this third one here. So as you will be able to see now, we will arrive at a new station and we will start the disembark process. So the astronauts that have this station as destination can leave, and those waiting in the queue to enter will be invited to get inside the cable car. Great. Now, the Brunel astronaut has a special destination. It is actually heading to Florida Polytechnic University's greenhouse. So as we can see, Brunel astronaut would live here and take the elevator down. And now it's on the path to get to the greenhouse door, where it will publish an interaction asking for the door to be opened, since the greenhouse has an R-lock system. So it arrived and it just sent the message asking the door to be open. So you can see the door is opening. And now the astronauts will be able to enter and produce the plants and biofuel, generating energy for the cable car system. And that's it regarding our visual demonstration. Before landing the presentation to FPU team, I just want to say thank you all so much for your attention. We are incredibly grateful to be part of this international collaboration. Special thanks to Paige for organizing the sessions and guiding us through the project. Opportunities like this ignite the passion for science in all of us. Now I'll hand it over to Florida Polytechnic University team, where Landon or some other team members will dive deeper into the greenhouse operations. Thank you.
Thank you, Kaike. So as you saw, the astronaut was able to enter the greenhouse by the door opening as it got close. We weren't able to put the Rankine cycle and irrigation systems in the Dawn simulation, but I can show the Unity simulation, which we got that working in, if it's okay to share my screen. Is that okay?
Yes, I'll stop sharing my screen now, Landon, so you can go ahead. And also, I will put in the chat some links to YouTube videos that showcase a little deeper the models that we developed and the behavior. But go ahead. Thank you, Landon.
Okay. So this is the simulation in Unity. As you can see, we have the greenhouse here on the foundation and the transparent windows, the staircase, and the door. Once it finishes loading, you'll see that I'm able to walk around with the first-person perspective. So I can navigate up the staircase here, and I'm prompted to interact with the door. This is the airlock. You'll notice that as I open this inner door, the outer door will close before the inner door opens. I can walk in here. Here we have the irrigation cycle with the mixing tank and the water tank for storing water for the aeroponics towers to irrigate the plants. I can grow cabbages or carrots. And then it'll show some irrigation statistics, such as the water production and the nitrogen production, with some of the cycle statistics down below. You'll see that the plants are starting to grow here. Meanwhile, we have the Rankine cycle generator back here that has statistics on the energy generated, which is supplying energy to the Fastens cable car system. And you'll see now that the plants have fully bloomed and in exaggerated speed just for purposes of demonstration. And that's all. Thank you.
Excellent. That's truly impressive job by those teams. Congratulations. Next, we have Genoa, if you would like to share anything about your Federate that's going right now.
Yes, actually, I prepared a demo in 1.5 minutes. If possible, I'd like to show.
Go ahead.
Okay, can you see my screen?
Yes, I can see your code.
Okay. This is the code in Eclipse we implemented, all running well. As you can see, time is progressing, update position and velocity. This is the lollipop. All Federate joining successfully. Time graph advancing, all time for Federate. And also we have some visualization in Dawn. There are some points I'd like to mention. first, the satellite is a scale. This is not the real size, therefore, because we like to show more obvious. And another point is the changing the reference terrain. For other teams, I guess it's a South Pole. We changed to moon-centric fix. And yes, this I think for future we work on more on orbital dynamics, have more complicated one. And this satellite goes for 70,000 kilometers, as I mentioned before. Okay, that's it.
Excellent. Thank you for showing and great job.
Thank you, everyone.
All right. Next, I believe we have IMT Minds, Little Catholic University, and UCF presenting together.
Yes, exactly. So I would like to start off with Dylan sharing his screen for his launch of the interactions.
All right. Okay, so I hope you guys can see Lars's manual control. We have both of our teams implemented a manual control system, which basically eases the way we display interactions and messaging. So for Lars, we have multiple options to communicate with other federates. So we can send a status of like the environment or surface scan to the landing beacon. We can also send environmental reports to us, and the next interactions are handled by the waste storage system, where they have like materials inventory. They also have waste, recipe lists, and other processes. And what Lars does is just request data from waste storage system, and then the waste storage system provides their inventory updates. So I believe we can start by sending an environmental report to the waste storage system. So that will be present as choice number. That will be number 2. Okay, and as you can see, we immediately send an environmental report to the waste storage system. And Lunar, if you can confirm that.
Yes, we did receive it. You'll see it in a bit on the share screen.
All right. And okay, I guess I could just go over the next functions and just briefly explain how they work, and then I can pass it over to you so that you can explain them in more detail. So option 3 is requesting a material inventory. And once I press that, we receive a material list from the waste storage system. So we have different materials with names and different material counts. Okay, the next option is to just exit the manual control, which we don't need to demonstrate that. Number 5 is to request a waste list from WAS. Okay, as you can see, we have a more comprehensive list of waste items, and then we can just move on to the next one. The recipe list, option 6. Okay. We have the recipe list. Okay. Number 7, pyrolysis options. Okay. We have the same list of wastes. And here we implemented another, just to customize the interactions even further. It's asking me to enter a waste number for pyrolysis. So the waste storage system is going to do is just going to perform pyrolysis for us. And when I press 2, we see that we receive pyrolysis results from WAS. Okay, and then a similar process is with decomposition. As the option 8, we receive the waste items, and then we enter a waste number for decomposition. So that will be, we can just do any number for now. Okay, we have received the composition updates, and lastly, we have the option to request recycling options from the waste storage system as well. and it's asking for an item number to fabricate. We can just press any of those and see what it returns. So Lunar, if you want to explain what's happening here.
Sorry, yes, do you want me to share my screen? It would, or actually no, you still have one more thing that we can do from your screen. So here what's happening is, so Dylan just sent a request for performing a recycling operation. So what happened is he sent a request for, if I'm not wrong, for the screw. So in that case, WAS receives a request for that and checks if there's enough material to make it. So in that case, there wasn't any iron in the storage database at all, and then there wasn't sufficient plastic. So we didn't go. So WAS doesn't go forward with that request and sends back an error. So we need more material. However, if we do try another one, which is for wire, that would work since we do have enough copper. So yeah, so we do get the message sent to Lars, and we have part wire with a certain ID, just for retrieval basically purposes, and basically that has been fabricated. Yes. Okay. So then, yeah. So do you want to show your other featherhead before I start mine?
Yeah, sure. So, all right. We also have, before we jump into EMT, we can show you how the messaging works. So for the landing beacon, I believe it won't let me show my other screen, but I can try. Oh. I'm just going to share my entire screen now. Okay. So I hope you guys can see two Eclipse windows, side by side. Okay, so I'm just going to send a message to the landing beacon again. This is number 1. And as you can see, we received it over here with position and surface analysis. We can send that again. Yeah. Okay, now we have the green messaging. And we also have the landing beacon receiving updates from the lander. And yeah, if anyone from my team wants to show the 3D models, feel free to do so. If not, we can just go ahead and jump into IMT's favorites.
All right, Manaf will be sharing the screen to show our 3D models. While we were not able to get full Dawn visualization, even though big thanks to Fastens and Kaike for including the beacon in the Dawn visualization. So as you can see, we have our Blender model right here. This is for the landing beacon, as Dylan just showed in the interaction. The landing beacon obviously has a satellite dish at the top, which is for transmitting the signals to the landers as well as to Lars. It has lights in the center for better visibility. It has a little panel right there down in the center of it, under the lights, that astronauts and others would be able to interact with for the purpose of configuration, and so on and so forth. And as you saw in the Dawn visualization, it's fairly large. It communicates with the lander that they displayed during their visualization. The second model is going to be Lars. As I mentioned, Lars is based off TARS, though it does look fairly different. We wanted to go with a more practical look and make it more of our own. It has a large center screen. The center screen is obviously interactable. It will display data for anyone who interacts with it. It will also be able to complete a number of different functionalities, as Dylan just showed, whether it be asking for recycling, material inventory updates, and so on and so forth. It has a number of sensors all around the sides of it. So you can see above the little Lars logo, a small sensor to kind of keep track of its environment and display environmental data, as well as sensors in the back, as well as the sides. And finally, the sort of movement we decided to go with was tank treads. Obviously, TARS from Interstellar uses like a really interesting, like 2 different kinds of legs to run around. That didn't seem nearly as practical, but the tank treads are fully functional. The wheels within the treads roll, and the treads themselves roll over themselves as it moves forward. So all but implemented in Dawn, we have full models as well as movement functionality.
All right, so do you guys still have anything to present, or can I jump into my execution?
You're good to go, Leonardo.
Oh, okay, thank you. So I'm going to share my screen now. All right, so can you all see my screen?
I can see it.
Okay, perfect. So I'm going to go over what Dylan just showed and the details of our side. So we also have a manual control implemented, but I'm not going to go over that since it's the same interactions that are going to take place just between the 3 feathers that we have. So this is the first interaction that Dylan just sent. So that's the environmental status report, so that we received directly. Then there was the basically the material list inventory request. So that was the sent message. Afterwards, there was the waste list request, which is this one. So just showing you what was sent. Then we received a request for a recipe list. However, the recipe list is not saved in the storage system, but in the transformation system. So in this case, we sent a message to the transformation system one. So it's here. And that's what we got. So got a request for recipe information, sending the list with the information. And then that was sent back to us. Then that was also sent back to Lars. And that's what we saw just previously. Afterwards, we got a pyrolysis request from Lars, which with the option, basically. So that was sent to the pyrolysis system, which we can see now. So here it is. So received a pyrolysis request from us for the following trash or waste. Opening the reflexive surfaces, getting ready for pyrolysis, the materials that were obtained, and then closing back the surfaces and shutting the system off. Whatever we got was sent back to the storage system since it works as a hub in the interaction. And then basically that's what we got from residuals. Those residuals were saved in the storage system. So carbon dioxide's amount increased, water's amount increased, and that message was sent back to Lars. Afterwards, we can see the decomposition. It's the same idea. So we received a message from Lars with the option. This is also what's shown in the transformation system. So that's the decomposition request with just updates being that decomposition is finished, and the results that were basically sent back to us. So that's the message that was sent. If we go back to the WAS interface or console, or rather, we can see the message that we received. The steel amount was increased, the copper amount was increased, material integration finished, and then the message was sent back to Lars as we saw before. And the last one was the recycling request. So we received one from Lars. However, what we received was for the screw, which we didn't have basically enough material. So again, another interaction between what and what's happened to get basically the recipe and check the requirements. So the problem was we didn't have enough iron nor enough plastic, and that was what was sent back to Lars. And then we got actually a interaction from from Catholic University. So that was the part or the waste that was sent. So we received a body, which I'll show how it was integrated in a bit. So body part received and stored. And then there was the last recycling request that was sent from Lars with the wire. So here we can see it. So that was number 3. Again, we sent a message to Watts to check basically if we have enough material. So it was enough. We received a message for fabrication being complete, and we got the ID with the part. So just to show you what we received. So so we need to print basically the waste. That's what we got from the ERRV Federate. So that's a new basically trash or waste that we got. And to show you as well what we got as recycled part, which is the wire. So this is what we got. So this is it for the code part and the console interactions. We will also show you just a basic graphics that was done with Blender and an animation, or basically a simulation of what happened. So it's just a minute and a bit. So yeah, so this is basically we chose to model the internal part of the storage transformation and pyrolysis systems. So here we can see that materials of the same type are being stacked over each other. And we can see here that basically just quickly a pyrolysis operation is happening. So the crane or the hand is basically just moving some kind of part to the burner that's being sent back to the storage. And after a bit, I'm just gonna skip to get the transformation going. So if we can see here, we already have some materials that are being basically handled. So these will be combined. So it's just a primitive simulation. So these will be combined and sent to where they need to be sent. So that's just the whole operation going. And I also have a quick video for just how the storage will look like once it's being filled. So stacks upon stacks of the same material will happen until, well, it's fully basically its capacity is at full. It's maxed out. So yeah, this is all from our team. Hope you enjoyed, and I want to say thank you for our collaborating teams. So UCF, especially Dylan, which we had direct contact with, as well as the team from Lead Catholic, as well as Paige for basically handling the tech tag apps and helping us through it. So yeah, that's all from us.
All right, congratulations, a great job to those 3 teams that just presented. I am Team Little Catholic and UCF. So I believe that concludes our Federation execution portion of the final event. Again, congratulations to all those active teams. That was a very difficult thing to do and very impressive accomplishment. So as I mentioned at the beginning, we do have a panel of experts that have been attending this session. So I'm going to hand it over to Zach Cruz and Simon, Simon being the executive chair of C, and Zach Cruz is here with me at NASA, but also is the founder of C. So I'm going to hand it off to them.
Hi, Paige. Hi, everybody. Zach, where are you?
Oh, there we go.
I'm here with Paige. Can you hear me?
Indeed. Well, last year I said that was the most impressive year C has ever had. I'm now going to upgrade my compliments for this year. That was significantly the most impressive results C has ever had, and you should all feel very, very, very proud. Now, I'm joined today by a panel of experts. So, as Paige has said, and brackets, I've got to say a special thank you to Paige. That I'm the executive chair. I'm a professor at Brunel University, and I've done modelling and simulation, particularly distributed simulation, for a very long time. And I've been involved in this also for a very long time. And I'm very proud that it's grown and growing and growing. So I'm joined with me, and I'll let the panelists introduce themselves. Zach Cruz, Mike Conroy, Crash from SISO, and I'll let Crash remind me of his full name in a second, and Professor Stefan Strasburger from Technical University of Ilmenau. So, gentlemen, if you can switch your cameras on. We were going to have another panelist, Dr. Anastasia Anignostou, who's representing ACM SIGSIM, but unfortunately she couldn't join us today. So each of the panelists are going to give you feedback on different aspects of the C event. And I'll start by, I'm just checking my list, I'll start by handing over to Zach.
All right, thank you, Simon. I want to echo Simon's comments on that. It was just a fabulous presentation. I think we got some feedback. Here we go. Okay, so we're gonna let me do a little bit of adjustment here. Okay, we're having some feedback in the room. Is that better? Okay, good. Yes. Okay, I just want to echo Simon's comments on this. This was just a spectacular C event. Just great interactions. I really liked what everybody did. I've got about 2 or 3 pages of notes that I took as we were going through this. I am not going to go through all of those for this. We don't have time. I just want to let all the teams know how impressed I was. And I also want to give special thanks to Paige and congratulate her on the amazing work that she did in bringing all these teams together. One of the focuses that I want to talk about, we've kind of got different ones that each of the judges are going to kind of focus on, is for me, one of the big advancements this year in the C was the infrastructure development. I think a special thanks to UCF, Mike Conroy and his group there for putting the new infrastructure in place. That is going to be, and it's an overused term, but it's really true here. It's a game-changing capability for the C events as they go forward, because now we're going to have an infrastructure that we can rely on year in, year out. It'll allow people to do development and testing throughout the year. They won't just have to wait until we get everything set up for the event. So there's a lot of amazing benefits out of that. And so I think that's just a phenomenal new capability that we're going to have, that we're going to be able to take forward. I did want to just to bring out a couple of favorites that I saw. I mean, there's so many of them. It was really hard to choose from. And I don't have time to go over all the different ones that I liked, the things I liked about each one. One of my favorites from last year was the Lunar cable car. I'm really glad to see that back again. I really like the advances that you made, the improvements in the interactions and the capabilities of it. I was definitely intrigued by the Lunar GPS, the LPS capability. I think there's some really interesting interactions that you can explore for next year, and understanding better how the other federates can take advantage of that. I do have some questions about the orbit chosen. I think the NRHO is probably not what you want, but I'd be happy to talk to you about that offline and what we've got. But just again, an overall congratulations to all the teams. What a fantastic display of your distributed simulation prowess and how you've gone forward. And so I'm going to stop my comments now, because I could go on for a while, and turn it over to the next judge. Thanks.
I'll say that again non-silently. On my list, Mike is next. Thanks, Zach.
Yeah, I guess just to add, or not add, to stand alongside, absolutely, completely, and totally blown away with every single aspect of everything. The Paige, awesome job too. This shows the work you had pulling people together and lining stuff up. What blew me away the most was the interactions across the board. The number of them that we had, how seamlessly they fit together, how that worked, and just the way they were presented, the way they were discussed, the way the information was passed. We don't have separate systems anymore. We've got a Lunar ecosystem, and it's represented in this SIM. That's absolutely fantastic. Infrastructure, yes, echo everything that Zach had. What the Don team has done, echo that as well. Cable cars, landers, just everything across the board was absolutely fantastic. It's hard to go single any one thing out other than how all of the teams worked together and how all of the teams pulled off what they pulled together. So it's kudos to all. Next.
The next on my list is Crash. Do we have a Crash? No, it's a strange thing to ask.
You changed the list, Simon.
Okay, well, let's move straight on to Stefan.
Yeah.
Oh, sorry, I have changed the list, yes.
That's okay. Okay, great. Well, folks, I'd like to give a few comments on the models and federates that I've seen in this C, and I have to admit that I'm probably the one with the least prior involvement in C and all, and so, but I do have to say I do have a couple of years of experience with distributed simulation and the HLA, couple meaning bit more than 25 years. Currently, I'm mostly doing HLA in teaching, but I also do a bit of research. And I must say that, let me tell you this, I'm really impressed of what I've seen today. Your models and federates, they are all quite impressive, and you can all really be proud of yourselves and proud of what you've achieved. And this actually really applies to all the teams that I've seen here. Well, of course, there are a couple of things that especially caught my eye, but of course these are obviously the visually impressive ones, the visually impressive models that catch your eye. But okay, I've made a few notes here. Okay, what did I see? I did see great lunar landers and spaceports. I was really impressed by the lunar cable car and the astronauts moving around. It's a great idea. And also the greenhouse and the satellites that were from some team. Yeah, but again, it's just a few observations here. Of course, the visually impressive ones, they really catch your eye. But being an HLA person, I also do know and I do appreciate the interactions between the non-visual federates. That's also really something I can relate to. The waste storage facilities and then the 3D model and its interactions with the what was it, the LARS and the landing beacon and so on. That was all really impressive. And guys, you can really be proud of yourselves. And I'm going to stop now. And I'm looking forward to seeing next year's exercise.
Thank you, Stefan. And now, in the correct order, over to Crash.
Thank you, Simon. I guess I feel privileged that I could be like Sting, just one word, and that's all that's necessary. Last name is Conwin. I'll give you a little bit about my background because I think that every perspective that I've had has made me more impressive with the results that you students have done and your mentor teams and your overall orchestrator Paige. Well done. My background, I was the director of defense modeling and simulation back when the HLA was first conceived by Judith Dahman as the chief scientist. I later was in charge of modeling and simulation for what's now the F-35 program, which is, the international multi-role stealth fighter. I was the chair of the NATO modeling and simulation group, the first chair.
where very much interaction is done for the purpose of worldwide peace and defense. And then finally, just a year and a half ago, I was the chair of the SISO XCOM. And so in all those roles, I look at the work that you've put together and shared today, and I find a couple things that I've watched since the first execution of this orchestration of events some many years ago now. I see much increased complexity. There are more items. There are more diverse items. They are have interactions. They are consistent with the standards for the surface of the moon. The time is standardized. You use the space farm. You use the high-level architecture. You use tools of the trade, all of which is very interesting. Parenthetically, I am the vice chair of a modeling and simulation standards body of knowledge. The target audience is you, next generation professional. And so if some of you are interested, I would like to have a user panel of some of you to say, what did you find most troubling? What information did you see that we can help put into a reference that will be available later? I wanted to celebrate a couple of the items. I saw proactivity on the parts of individual teams, individual members, and reaching out to go to that next level of excellence, as well as to that next level of complexity with some of your teammates. Another thing that I celebrate in the people that I hire is I look for people with lifelong learning. I would like to say that what I observed in this short interview was the interpretation that not everybody came to the table with a complete bag of tools to apply to the problem, but you studied, you applied yourself, and you produced some remarkable results. And then finally, mission orientation. When I say mission orientation, take the mission of your organization as your own. In this context, I would say that it's teamwork with a purpose, and the purpose was to have a reasonable synthetic environment that exploration and engineering can be done. So I'm going to leave you with a quote that I think C personifies. Tell me, I forget. Teach me, and I may remember, but involve me, and I learn. Thank you, Paige. Thank you, teammates. Thank you, university mentors. I am really privileged to be part of the evolution of C. Thank you again. That's it.
Thank you very much for that. And thank you for all the panelists and their feedback. And just to underline that, I'm just sort of scratching out some numbers. Approximately, we had 16 operational federates from 10 teams spanning 7 countries, and something in the order of 80 to 90 participants. Several teams mentioned one of the greatest experiences in doing C this year was teamwork. Just taking a step back, I don't know of many enterprises, and I'm thinking of academia and industry, where so many people have worked together to achieve something that spans so many different countries. You should all be extremely proud of yourselves. You've produced some incredibly impressive work, and thank you for allowing us to see it. And I'd also like to praise Paige for chairing this year's C and doing another fantastic job. And I've got to say ACM SIGSIM have provided some funding to enable some of the infrastructure transition this year. We hope SIGSIM will be able to continue that. So I'll hand back to Paige. Paige, I'll say something about WinterSim, but would you like to close things off formally?
Sure. Thank you very much to our panelists for attending. We really appreciate you being here and giving some feedback to our teams. I'll turn my camera on briefly so you guys can also see my friendly face. Congratulations again to the teams. This was very amazing accomplishment. I'm glad you got the chance to show it off. Some great ideas, some great simulations. So officially C 2025 is now closed, and we invite you all back for next year. So congratulations.
Thank you, Paige. And we're just doing something slightly differently this year. So I'm chairing the annual Winter Simulation Conference. This year it's in Seattle. ACM 6 Sim has very kindly offered 3 travel grants of around about $1,000 to enable representatives from teams to come and join us there. You need to be able to write something, so we need at least a 2-page abstract, if not a full paper. And the idea is that you'd come together for one session in Seattle, present, and then we'd decamp to the exhibitors hall to try and set up some sort of demonstration of what we did this year. So any team representatives who are interested, please get in touch. I know Brunel's interested. I know Fassens is interested, but if anybody else would like to reach out, that would be great. And if we end up having 2 or 3 more teams being interested, then I'll try and negotiate something from 6sim. So please let you know Paige more than I do. So please let Paige know, and Paige will let me know. And again, congratulations, everybody.
All right, thank you, Simon, and we look forward to being at the Winter Simulation Conference this December shortly. So thank you again, everyone. I had a great time being your technical chair again this year, and we look forward to seeing you back for CE 2026 next year. Thank you very much, and congratulations.
Thank you, Paige.
Absolutely awesome, everyone.
Yeah,
Great job.
Awesome. Thank you.
Thank
Great
you.
job, folks.
Great.
Awesome. Thanks, everyone.
Thank you, Paige.